Hello and welcome to the next video in our series. This is Essential Skills for Physical Science, helping you get really well prepared for Paper 1, the physics paper. I'm Dr. Derek Fish. I've been Director of Unizulu Science Centre at the University of Zululand for the past 30 years. This is video 6.2, continuing in our section looking at the skill of equations, looking especially at Newton's second law, which is always question 2, the first long question in your matric paper. You'll find this in your booklets on pages 42 to 47. But before we turn to page 42, as we always do, let's start at the beginning. Please go to page 3, just inside the front cover of your booklet. Let's look at the contents page to see where this section fits in. Remember, this is essential skills. We're considering 5 skills for physics: graphs, free body diagrams, equations, multiple choice, and ratio questions. And we're looking specifically at the equations section here. Now, you will also need to look back at the free body diagram section, because you can see that also covers questions that come up in question 2 in the physics exam. Just to expand on the equation section, we're looking at equations dealing with Newton's second law specifically. Question 2 in the paper and 6 pages from page 42 to 47. Again, why are we focusing on skills? Because here's a comment from the National Examiner: learners still cannot work with scientific equations and formulae. And that's why we're spending a lot of time looking very specifically at all the different equations in all the different long questions. Turning to page 4, remember again, you can always see the page number in the bottom right-hand corner of my screen, and that corresponds to the top right-hand corner of your booklet. So of course, this is part of the mechanics section, and this is actually something that comes mostly from grade 11. You can see in grade 11, we have here Newton's laws and the application of Newton's laws. So 4 laws in all: Newton's first law, second law, third law, and his law of universal gravitation. So we're focusing on different kinds of forces: weight, normal force, frictional force, applied forces, tension, and looking at force diagrams, free body diagrams, and the applications of Newton's laws. There's a prescribed experiment, which is the relationship between acceleration and force and mass. Now, you do also need to go back to grade 10. When you were introduced to vectors and scalars, you looked at one-dimensional motion and acceleration and so on. It's important for you to look at that as well. And there's a little bit of Newton's second law in grade 12, in that Newton's second law can be expressed as the rate of change of momentum. So the top of page 5, don't neglect your grade 11 physics, because Newton's laws that comes up there is very important, and most of question 2 is based on grade 11 work. Again, a comment from the examiner: grade 10 and 11 work is poorly understood, and this work should be integrated with the work done in grade 12. So it's time to wake up. Now, looking at the exam paper, remember we've averaged the marks per question for the last 3 matric papers. Question 1, multiple choice, is always 20 marks. Question 2, which is the Newton second law question, on average has been 17 marks. So it's one of the longer questions, and it's usually counted for 17 marks. Here's a snapshot of the last 3 questions. I want to tell you that students very often find question 2 very difficult. And unfortunately, it's the first of the long questions that you will encounter. But fear not, because we have a strategy which is proven to help you with this. So keep watching, and we'll show you how to take the fear out of question 2. What skills will you need? Also on page 5, remember these are the CAPS skills, and really there's a whole lot of the skills you'll need to answer question 2. You'll need to know scientific notation, especially if doing gravitation questions where you've got very big exponents, like for the mass of the Earth, very small exponents, like with the universal gravitational constant. You need to be able to convert units, meters, kilometers, and so on. Change the subject of a formula to solve equations. Trigonometry is important, because there will usually be components of a force in terms of the sine and cos of an angle, fractions and ratios. Rate is important because, of course, acceleration is just the rate of change of velocity. Direct and inverse proportion, especially Newton's second law, acceleration is directly proportional to force and inversely proportional to mass. And then constants. We've got a small g for the acceleration of gravity, a big G for the universal gravitational constant, and others. Now again, comment from the examiner. A severe lack of skills is evident. Which skills? Mathematical, conceptual understanding, and integration of topics, free body diagrams, graphs, and equations. So that's why I'm here, to help you assimilate the skills that you need for success in paper 1. Let's have a look at some of the basic theory concerning Newton's laws of motion, and in particular, Newton's second law of motion. Once again, may I remind you that this is an essential skills series. I cannot replace 2 years of teaching with a few hours of video. So please make sure that you go through your textbook, your notebook, and talk to your teacher about this big section of grade 11 work. I will simply skim through some of the most important theory. So we're going to learn all about forces here. And a really good way to do that is with this wonderful simulation from PHET called Forces and Motion Basics. The first part of the simulation is a tug-of-war competition between the blue team and the red team. And it's a good way of learning, first of all, about Newton's first law of motion. Newton's first law says if there's no net or resultant force, then velocity will either stay zero or be constant in a straight line. Now you can see this cart in the middle, which can be pulled by the teams, is not moving. The speed is zero because the sum of forces is zero. In fact, even if I put a strong man as anchor in each team and I allow it to go, they can pull as hard as they like, but there's still no movement because the sum of forces is zero. So we see Newton's first law of motion here. An object at rest remains at rest unless acted on by an external resultant force. Let me add one person to the blue team, and you can see immediately if I allow it to go, we now have a resultant force to the left, so the object moves to the left. Now I can balance this so that now the sum of forces is zero. And in many cases, you might consider that when I allow the simulation to go again, that the object should stop. But remember, it was already moving to the left. So in fact, it keeps moving to the left at constant velocity. And that's what Newton's first law of motion tells us. It's not enough just to balance the force. If it's already moving, it will continue moving in a straight line with constant velocity. So once again, when the forces are balanced, there'll be no movement. If I unbalance the force to one side, it's not enough simply to balance it. I have to add a greater force so that there's now a net force to the right-hand side. That can allow things to turn, so the red team starts winning. And if the blue team simply balances the force, it's not enough. The cart will continue moving at constant velocity in a straight line. And in this case, the red team will win. So there you saw Newton's first law of motion very nicely illustrated. And of course, when the two sides are unbalanced, then you see the second law, that an unbalanced force causes an acceleration in the direction of that force. Now, we can also look at this section, which is the acceleration section, which allows you to apply a force to an object. And we can ask it to tell us all kinds of things, the masses, the speeds, the accelerations, and so on. And once again, let's switch off our friction so that there's no external forces. Again, let's look at Newton's first law of motion. So this object is sitting here. There's no resultant force on the object, and so the object doesn't move. If I apply a resultant force, so let's maybe give it 100 Newton force, you can see it now has an acceleration of 2 meters per second squared, and the speed is increasing. So this is now Newton's second law. But if I switch off the force, then now sum of the forces is zero, the speed stays constant, acceleration is naught, but the object continues moving at constant velocity. See, the speed is constant, in a straight line. So this is an illustration again of Newton's first law of motion. So let me just recap Newton's 3 laws of motion for you. First law simply says that everybody remains in a state of rest or uniform motion unless acted on by a net external force. So if F net is naught, then acceleration is naught, then velocity will be constant, and that's in magnitude and in direction. But if the net force is non-zero, then the acceleration will be non-zero, and then it's governed by Newton's second law of motion. The acceleration produced by the force is directly proportional to the net force, inversely proportional to the mass of the object, and will be in the same direction as the force. Newton's third law is the force of action-reaction. It simply says if A exerts a force on B, then B exerts an equal and opposite force on A. So that's just a very quick recap, but please do spend some time going through Newton's laws more thoroughly. Once again, let's just investigate Newton's second law using the PHET simulation. Now we understand that this is a simulation rather than a real experiment, but it is still useful. The moment we have Newton's first law, no net force, so no movement. Let's switch friction off so we don't have to deal with that. So we're going to allow this person to exert a force on the box, and we're going to see what the acceleration will be. So let's increase the force to 50 newtons. Acceleration is 1 meters per second squared. The speed increases slowly. Double the force to 100 newtons and the acceleration doubles. 150 newtons, 3 meters per second squared. 200 newtons, 4 meters per second squared. What we can see is that the acceleration was directly proportional to the applied force in the absence of friction. Let's restore things again. Now let's have look at the effect on acceleration of mass. So we'll start off with a very large object with this fridge here, and maybe even with these 2 boxes on top of it. Again, we'll switch off our friction. So we've got a very heavy object, which is difficult to accelerate. So let's apply quite a large force of 200 newtons. We'll leave that force constant. You can see the acceleration is very small, 0.67 meters per second squared. Remember that. Let's lighten the load. So now the total mass is 250 kilograms. Allow the man to push with the same 200 Newton force, and it's now 0.8 meters per second squared. Let's lighten the load again, same force, and it's now 1 meter per second squared. Let's remove our 200 kilogram fridge, rather make the total mass 150 newtons. Doesn't matter what the objects are, as we're not considering friction. And again, our 200 Newton force, and you can see we now have 200 Newton force. We have an acceleration of 1.33 meters per second squared. Remove those blocks, and we now have again a 200 Newton force on 100 kilograms, 2 meters per second squared. And you can see as we continue to make the object lighter, but continue with the same 200 Newton force, you can see what happens. Now the acceleration is 4 meters per second squared. Now comparing this with the fridge that we started with, we can see that acceleration is inversely proportional to mass. Now we can do a proper experiment for this, which I'll tell you about in a minute. It's also important for you to understand forces on an inclined plane. And there's a very nice simulation called ramp forces in motion, included in your teacher pack, which we encourage you to explore. I'm not going to redo this now, because this was done very extensively in video number 5 on free body diagrams and forces. And on page 33, this diagram about the normal force on a slope. It's very important, but as I say, you can see it on page 33, or it's covered very extensively in video 5. Having spent some time trying to get a conceptual understanding of forces and Newton's laws, let's move on to the main purpose of this video, which is looking at the equations and the variables. So in your booklets, we're at the top of page 42. So the Newton's laws equations deal with 10 different variables. Some will be familiar to you, some may be not so familiar. I want you to notice that the first 5 of these 10 are actually all forces. And you can see each one is measured in newtons. So they're just different types of forces. F is just force, as we know by now, but we often talk about the net force. So F is a subscript net. N is the normal force, also in newtons. And you can see on page 33 for more about the normal force. This came up in video 5 on free body diagrams. W is the weight in newtons. It's the force with which the earth attracts a body that has mass. And then you've got 2 frictional forces. Now at the end of this video, we will spend some time with them, but static friction is a frictional force that exists before an object starts moving, and that has a certain maximum value. Whereas kinetic friction is a constant, and that's the force of friction that exists when a body is already moving. That's always less than the static friction. You know by now, it's harder to push start a car to get it started than to keep it moving. Then you've got 2 coefficients. They don't have units because they're just numbers. Coefficient of static friction and coefficient of kinetic friction. Now those are constants which depend on the surfaces in contact with each other. If you've got sandpaper on sandpaper, they'll be quite high, but if you've got smooth surfaces together, they will be lower. Mass is measured in kilograms. Just remember to convert if it's given in grams. Acceleration in meters per second, and r is the distance between bodies. Sometimes it's called d, and that's measured in meters. Now again, please make sure you convert. That will often be given in kilometers, and then you need to multiply it by 1000. Now there are also 4 constants that we use in question 2 and dealing with Newton's second law and law of gravitation. The acceleration due to gravity on Earth is 9.8 meters per second squared. Now, just to give you an idea of the size of these numbers, I've just written them out fully in red. Obviously, that's just 9.8. Big G is the universal gravitational constant that we use in Newton's law of universal gravitation. 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And when we write that out, we find that's a very small number with lots of zeros at the beginning. M is the mass of a planet, and the specific example we have is the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. Now that's a very large number, so lots of zeros after the number, because of course the Earth is a very massive body. And finally, r is the radius of the planet. Specific example is the radius of the Earth, which is 6.38 times 10 to the 6 meters, or about 6,380 kilometers. Now, because the universal gravitation constant is so small, you don't get a significant gravitational force unless the masses involved are quite large, and that will become quite important. Let's look at the different equations you will be using. These will obviously be on your data sheets, and remember these are on page 38 and 39 of your book. So turn back to page 38, and the Newton's laws equations are the second block of equations at the top of page 38, and they're under force. So you can see there's 1, 2, 3, 4, 5, 6 equations which are important. The other ones are for momentum, as we've seen, or otherwise just different versions with D instead of R. Basically, the ones I've circled in red have to do with Newton's second law, F net equals ma, or weight equals mg. The ones in blue have to do with friction, static friction and kinetic friction, and the ones in green have to do with Newton's law of gravitation. Now, these are all important, but I want to tell you most of your work will be done simply with this Newton's second law equation. F net is equal to ma, and you'll find most of the long calculations with 7 or 8 marks, the solving equations, will go around this particular equation. So we're going to spend some time making sure that we really understand it well. So we will look at the equations in 3 different groups: Newton's second law, then friction, then gravitation. But as I said, the Newton's second law is by far the most important in terms of question 2 in the exams. So we're on page 42. And Newton's second law is usually quoted as F equals ma. But actually what Isaac Newton said is that acceleration is directly proportional to net force and inversely proportional to mass. So let's look at the first part of that. Acceleration is directly proportional to net force. Now this makes sense to us. The more people you have pushing a car, the more force you have, the greater the acceleration is going to be. So if you have two objects of exactly the same mass with a larger force, we get a greater acceleration. With a smaller force, we get a smaller acceleration. So they are directly proportional. We get a straight line graph, which goes through the origin. Of course, acceleration is our dependent variable, and force is our independent variable. But we get something very different when we consider acceleration, how it relates to mass. And as Newton says, acceleration is inversely proportional to mass. So we actually get a hyperbola, different graph completely. So if you have a small mass and a reasonably large force, you get a large acceleration. Small mass, large acceleration. If you have a large mass and the same force, we get a large mass, we get a small acceleration. Now again, that makes sense to you. If you're trying to push start a car, you're much more likely to succeed than trying to push start a truck, which is much heavier. Now, there is a prescribed syllabus experiment to do Newton's second law of motion, and we have done it and put it on this series as an extra video. But I have to say this hasn't been examined for the last 7 years, and it doesn't seem likely to be. So please feel free for completeness to look at this, but we haven't included it here because we are focusing on skills for paper 1. But we do go through the experiment very carefully. We've videoed all the different parts of the experiment, and you'll be able to conduct it. So we encourage you to make use of this. So let's consider this equation, F net is equal to ma. Now, when you're using Newton's second law in this form, there's some things that you should be careful about. Number one, make sure you've taken account of all the forces shown. And drawing a free body diagram will help with this. And question 2.2 is nearly always a free body diagram. And this will help you to take account of all the forces. Secondly, make sure you've considered forces which may not be shown, like gravity or the normal force. Number 3, make sure that the force which causes the acceleration is the net or resultant force. That's why we write F net equals ma. Number 4, make sure you've accounted for all the mass being accelerated. And finally, when you're on an inclined plane, and you can see this is done very carefully on page 33 in your booklet and in video number 5 on free body diagrams, make sure that you correctly identify forces and their components when on an inclined plane. Now, if you turn to page 43, there's some exercises to test these points above. And we'd like you to pause or stop the video here for 10 minutes while you try to complete the 5 questions from B to F. I'll do A with you now, but it's really important that you pause the video, try to do these yourselves, and then we will mark them. So please take note, in each of the 6 questions, you're to calculate the acceleration of the 2 kilogram mass, the same in each question. Secondly, to simplify calculations just on this page, take g equal to 10 meters per second squared. That's very close to 9.8, and it's fine as an approximation just for these questions. Obviously, in the exam, use the constant sheet. And finally, assume that there's no friction on the surfaces or the pulleys unless friction is shown, like in number F over here. So let's look at A. You've got a 2 kilogram mass being pulled by a 30 Newton force on a frictionless surface. So very simple, acceleration equals force over mass. 30 newtons over 2 kilograms equals 15 meters per second squared. You can just give the magnitude, don't worry about the direction. So I'd like you to pause the video here for 10 minutes, and you can just work in these boxes and try to calculate the acceleration of the 2 kilogram mass in every one of these other examples. I really hope you've tried all of them. First of all, I'm going to give you the answers. Let's see if you got 6 out of 6. In B, the acceleration of the 2 kilogram mass piece will be 5 meters per second squared. In C, it'll be 6 meters per second squared. In D, 2 meters per second squared. In E, 3.33 meters per second squared. And in F, 2 meters per second squared. Now, maybe you're feeling a bit puzzled now because probably you didn't get 6 out of 6. And these can be quite tricky. So let's go through the answers slowly so that you can understand where you went wrong. Please don't feel bad if you went wrong. Science is all about going wrong and learning from our mistakes. It's nothing to be ashamed of. And all the great scientists spent their time making mistakes, but learning from them. Let's look at number B. Now, remember, we said when you use Newton's second law, you need to ensure these 4 things. I've just left out number 5, which has to do with an inclined plane, because we're not dealing with it here. So maybe you looked at this and you said, no problem, it's just like number A, acceleration is force over mass, 30 newtons over 2 kilograms is 15 meters per second squared. If you said that, I'm afraid to say you are wrong, because you didn't read carefully these 3. Have you taken account of all the forces? Have you considered forces which may not be shown? And of course, there's the force of gravity, the weight of this 2 kilogram object, because mg is 20 newtons, just using our approximation of g equal to 10. So we need to make sure that the force which causes the acceleration is the net or resultant force. So let's try this one again. Acceleration is F net over mass, which is 30 minus 20, 30 newtons up, 20 newtons down, divided by the mass of 2, which is equal to 5 meters per second squared. If you got that, well done. If you got 15 and are feeling bad, please don't worry about it. At least you found out now. Rather get it wrong now and get it right in November. Let's have a look at number C. So you've got a frictionless table. You've got a 3 kilogram mass hanging over a pulley attached to the 2 kilogram mass by a string. Now, hopefully you've learned from B. So you're saying to yourself, I'm not going to ignore the force of gravity. So there's a force of 30 newtons pulling this mass piece down, and it'll obviously be transmitted through the string to pull the 2 kilogram mass piece whose acceleration I want to calculate. So easy, acceleration equals force over mass. 30 newtons is pulling on the 2 kilograms is 15 meters per second squared. No, because in this case, maybe you want to try it again and say, actually, it's not pulling on the 2, it's pulling on the 3. So let's divide by 3. We get 10 meters per second squared. Again, no. So what have we neglected? We have taken account of all the forces because only the 3 kilogram is being pulled downwards and there's no friction. But what we haven't done is accounted for all the mass being accelerated. Because these are tied together by the string, they form one system. And if the 3 kilogram is accelerating, so is the 2. So in fact, to calculate the acceleration, you have to take the net force of 30, divide by 3 plus 2, the mass of the whole system, which is 5 kilograms, and that gives you 6 meters per second squared. So that's the right answer here. It's tricky, but let's learn from it. Number D, this is known as an Atwood machine. You've got a pulley with a 3 and a 2 kilogram hanging over it. As you can imagine, the heavier 3 kilogram mass would pull down and the 2 kilogram would be pulled upwards. Again, we know that there's a weight on the 2 kilogram mass of 20 newtons. And so we could say, right, acceleration is force over mass, 20 over 2 is 10 meters per second squared. No, then you're ignoring the string and the 3 kilogram on the other side. So you haven't taken account of all the forces shown because we have another force over here, which is the weight of the 3 kilogram mass piece. We need to make sure that the force causing the acceleration is the net or resultant force. So the 2 kilogram experiences 20 newtons down and 30 newtons up. So let's try again. Acceleration is net force over mass, 20 minus 30 over 2. Don't worry about the sign. We just want the magnitude. That's 10 over 2, which is 5 meters per second squared. Again, No. Why? Because we haven't accounted for all the mass being accelerated. We're acting like only the 2 kilogram is being accelerated, but of course both of them are being accelerated. The 2 goes down, the 3 goes up, but they're both part of the system. So let's try again. Acceleration is F net over mass. 20 minus 30 over 3 plus 2 gives us 10 over 5, which is 2 meters per second squared. So I hope these examples are showing you why these things that you need to ensure are so important. Let's look at E. Again, we've got pulleys. The 2 kilogram is being pulled in both directions. And we know that there's the weight of the 3 kilogram mass. So there's a 30 Newton force pulling down here, which of course will pull the 2 kilogram to the right. So let's try. Acceleration is force over mass. 30 over 2 equals 15 meters per second squared. But no, this is not the same as example A, because have we taken account of all the forces and have we considered a resultant force? No, but it's also a 10 Newton force down because of the weight of the 1 kilogram block. So in fact, we could try again and say it's 30 minus 10, 30 to the right, 10 to the left, divided by the mass of 2 equals 10 meters per second squared. Again, no, because we haven't accounted for all the mass being accelerated. And you should know by now that if 1 and 2 and 3 are joined together by strings which can't stretch, they form one system, and the total mass being accelerated is actually 6 kilograms. So we've got a net force of 20 newtons to the right divided by 6. The total mass is 3.33 meters per second squared. So that is correct. Finally, number F. Again, 3 and 2 joined over a pulley, in this case, a force of kinetic friction to the left of 20 newtons. So this 2 kilogram mass is lying on a rough surface. So by now we know not to neglect gravity. There's a weight of 30 newtons pulling down on the 3. I'm pretty sure that there aren't any other forces of gravity which are important. So we can say acceleration is force over mass, 30 over 2, 15 meters per second squared, but no, because we haven't taken account of all the forces. And there's a frictional force here, which is opposing the gravitational force. So let's try it again with the net force. 30 to the right and 20 to the left leaves a net force of 10 newtons divided by 2 kilograms equals 5 meters per second squared. Again, no, because we haven't accounted for all the mass being accelerated. We need to divide by 5 because the 2 and the 3 are both being accelerated, and that will finally give us the right answer of 2 meters per second squared. So maybe you found that quite confusing. And Newton's second law can be confusing. It took someone as great as Isaac Newton to discover it. But that's the beauty of video. You have the booklets, you can try the examples again, and you can rewind and watch it again. Of course, we were just doing the examples very quickly, as one would for multiple choice. When you do the examples as part of the longer questions, you need to do them much more carefully without making approximations and carefully considering the forces on each object. But don't worry, we're going to get to that. So let's have a look at the equations related to question 2, which specifically deal with friction. Now, of course, when you look at things microscopically, you get a very different picture. Two surfaces that might seem smooth to us at a microscopic level are not smooth at all. And that's where friction comes from. Now, as we mentioned to you on page 38, when you look at your data sheets, these are the equations for question 2. And probably the most important one, Newton's second law, but the two we've outlined in blue are for friction. You'll find them at the bottom of page 44 in your booklets. But as usual, before we get to the equations, let's make sure we understand what friction is. And we'll use the simulation from PHET. Here you can see a chemistry book on top of a physics book, and there's some friction between them. And when chemistry and physics gets together, there's normally a bit of friction. If I move the chemistry book, but keep them well apart, you see, because the molecules are not in contact, there's no friction. But if they're pressed together by the weight of the book and the normal force, you can see as I rub the surfaces together, the molecules start getting very agitated, They start moving faster, their average kinetic energy increases, and we see a rise in temperature. So that's what friction does. It converts mechanical energy, like kinetic energy, into thermal energy. Now, of course, because that heat is just radiated away, it's not useful, and we say we've lost energy. What we really mean is it's converted into forms that we cannot use. Now, your equations on page 44 are for two different types of friction, static and kinetic friction. The meaning is obvious. Static means standing still, and kinetic means moving. Sometimes it's quite hard to understand what these mean, but we'll understand a lot better with the use of the simulation from PHET. It's called Forces and Motion Basics. And as always, I encourage you teachers to make use of this to explore it by yourself and with your class. So this simulation allows me to apply a force, which you can see here, onto an object. I can check the mass. This is a 50-kilogram box. Then we put a 40-kilogram child on top, so we have combined 90-kilogram object. We have an accelerometer, which will show whether it has a positive acceleration to the right or negative to the left. And we have a speedometer, which will show the speed of this object. At the moment, there's no applied force, there's no movement, there's no acceleration. Finally, we have set that there will be friction. You can see this is a rough surface, quite a lot of friction, but not so much that we can't move the object. So let me apply a force to the box. We'll start off with 50 newtons, then 100. Nothing is happening. And you've all had this experience when you try to push a heavy box, but your force is not enough to overcome the frictional force. Now, this is a static frictional force. You noticed it's changed. It was 50, now it's 100. And up to the maximum, the static force of friction simply matches the applied force. They're equal and opposite. The sum is 0, so no acceleration, no change in speed. I can increase further, 150 Newton applied force, 200 Newton applied force, but this frictional force in the opposite direction just matches that. Now, this doesn't happen forever. We reach a point where the applied force is greater than the static force. This static frictional force is about 210 newtons. And you can see if I increase my applied force to 250 newtons, we now have a resultant, the sum of forces. So there is an acceleration, and you see the speed is increasing. Now notice the frictional force has actually dropped. It's 169 newtons. It went as high as 200. And it is constant. If I increase my applied force, it doesn't matter what that is. The frictional force, which is the kinetic frictional force, is actually constant now. And so you can see a big acceleration, big increase in speed until this poor man can't keep up and push anymore. So now the applied force is naught. So the only force is a frictional force, which acts in a negative direction. So you see a negative acceleration, a deceleration, and the speed is decreasing all the way down to 0. So I hope that helped you to understand the static friction, which opposed the motion when I started pushing, and then the kinetic friction, which took over once I'd got more than the maximum force of static friction. Of course, you can also put the friction down to nothing here. It's now as if this box is on an ice surface, and then even the smallest force applied all goes into accelerating the object. There's no frictional force, and we don't need to worry about static and dynamic friction. So always read a question carefully and see whether it does indicate a force or not. Of course, in the real world, this never happens, that there's no friction. We are always fighting to overcome the force of friction. So let's get to the equations now. As I said, they're at the bottom of page 44. Please go there in your book. Let's start with static friction. Remember, when we started pushing the box, the static frictional force simply matched the applied force up to a certain maximum value. The motion will not begin until the applied force is greater than the maximum force of static friction. So F applied must be greater than Fs max. S for static, max for the maximum. Now, static friction is given by mu s times n. N is the normal force that pushes the surfaces together. Obviously, the harder they push together, the greater friction will be. And mu s is simply a constant, and it's just the coefficient of friction which depends on the particular surfaces in contact with each other. If you had two pieces of sandpaper together that were very rough, it would be high. If you had two pieces of glass together that were very smooth, it would be low. Now, in this picture, when we started, the applied force was less than Fs max, so there was no motion. Once we increased the applied force to 300, we noticed something interesting. The frictional force actually dropped, and it became constant. So once motion has started, a constant force of kinetic friction is experienced. That's given by Fk equals mu k times n. And in this particular picture, the applied force is greater than the force of kinetic friction. So the sum of forces, it's a simple subtraction, equals 300, the applied force, minus 169, the force of kinetic friction, equals 131 newtons. And that is F net. That is a net or resultant or sum of forces which is available to accelerate the object, causing this increase in speed. Now just note, static and kinetic friction, they both oppose motion. So you can see the motion was to the right in each picture, and the frictional force was to the left. So let's have a look at the equations that specifically deal with gravitation. Again, as we said from your data sheets, you can divide up the equations into three groups. Newton's second law of friction. The ones at the bottom highlighted in green deal with gravitation. Of course, we need to add weight equals mg as well to that. So Newton's law of gravitation, this amazing scientist Isaac Newton was responsible for his three laws of motion and his law of universal gravitation, which really changed the world by helping us to understand gravity and being able to plot the motion of planets and things like that. Now, it's an example of an inverse square law in that the force that M1 exerts on M2 is proportional to each of the masses, but inversely proportional to the square of r, which is the distance between their centers. Now, this looks very much like Coulomb's law of electrostatic force, which you can find on page 58 under the section on electrostatics. And you see the format of the law is very similar, with Q for charge in place of M for mass. Big difference, of course, is gravity only attracts, whereas a Coulomb force can be attractive, like between protons and electrons, or repulsive, like between two protons. Imagine if gravity could be repulsive as well. It would be very difficult to live our lives on Earth. Now, an inverse square law, just graphing it, shows you how quickly these forces decrease. So gravitation and electrostatic force get small very quickly as you move away from the source. And so this red line here is a plot of the relative intensity at different distances from the point source. You also experience this when you're standing close to a fire to get warm on a cold night. As you walk away, that heat gets less very, very quickly. So just for comparison, the dotted line is F proportional to 1 over R, a hyperbola. But in fact, these forces are proportional to 1 over R squared. I just wanted you to see just how quickly that gets smaller. Maybe one way of thinking of it is that the force from the source, whether it's gravitational or electrostatic, has to be spread over a whole area. And that's why it depends on the square of the distance and not just the distance, because we're looking at an area rather than just a line. So some points to note about Newton's law of gravitation. We're on page 44 in your booklets. So when you do any calculations, just remember these. Number one, force is a vector and it must be given a direction. But one can often just say that the force on M1 is to the right or towards M2. Secondly, the two forces experienced are equal and opposite. So they have the same magnitude and opposite direction. And Newton's third law of motion says that must be so. Thirdly, gravity only attracts. It can't be repulsive like an electrostatic or magnetic force. Fourthly, as the bodies are often large, like the Earth, you measure the distance apart from their centers. From the center to the outside of the Earth is over 6,000 kilometers. And so you need to measure distance from the center, which is also the center of mass. Then finally, the constant, big G, the universal gravitational constant, is very small, 6 times 10 to the minus 11. So gravitational forces are only measurable between very large masses. So you might like someone and be attracted to them, but I want to tell you the gravitational force between you is insignificant. So again, there's a wonderful way to explore this with the Gravity Force Lab, one of these great PHET simulations. And you can see you've got two masses which are attracting each other. Now you can see the force of attraction from the length of these arrows or from the numbers on top. Let's change it to decimal notation. Although these are quite heavy objects, 170 kilograms and 380, you can see the gravitational force between them is extremely small, less than 1 part in a million. But what you'll notice is as I make mass 1 bigger, you'll see the force increases. So it's directly proportional to M1. As I make M2 bigger, the force increases, so it's directly proportional to M2. And as I move them further apart, can you see how quickly the force gets smaller? And if they're this far apart, you can see you've now only got a tiny force between them. If I bring them close together, because of that inverse square effect, the force becomes much, much stronger. So let's talk about the weight equation in the middle of page 44 in your booklets. Weight equation says weight, which is the force with which the Earth attracts an object, or any planet, in fact, is equal to m, the mass of the object in kilograms. Please note that, times g, the constant for the acceleration of gravity, which on Earth is 9.8 meters per second squared. Now, people get very confused between mass and weight. Let's say you have a parcel, a box, which has a mass of 10 kilograms. Whether you're on the Earth or on the Moon or in free fall in the International Space Station in orbit around the Earth, the mass would still be 10 kilograms. The only way you can take away the mass of something is to physically remove parts from it. Now, the problem is that most of the bathroom scales and the weigh scales we use on Earth are actually measuring weight, not mass, but they just convert it to kilograms because they don't expect to be used in space. And so that conversion is quite valid. So on Earth, this 10 kilogram parcel on weigh scales would show a mass of 10 kilograms, but it's actually converting from a weight of 98 newtons. 10 times 9.8 equals 98. Now, the Moon is much smaller than the Earth, and gravity on the Moon is only 1/6 of what it is on Earth. So your weight on the Moon, the force with which the Moon attracts this box, is only 16 newtons. So this weigh scale would wrongly read 1.6 kilograms. Now, of course, if you were in free fall, like in the International Space Station, I'm sure you've seen videos of astronauts floating around. It's not because there's no gravity. In fact, the Earth's gravity keeps the space station in orbit. It's because they're in free fall, like being in an elevator when the cable snaps and you fall freely towards the Earth. So this box is unable to press down on the weigh scales because they're both falling freely. So the weigh scales would measure 0 kilograms because effectively this box in free fall in space is weightless. Now, how do we know that gravity on the Moon is 1/6 what it is on Earth? Well, we can put together Newton's law of gravitation and the weight equation. So there's the weight equation. The weight of an object with mass m equals mg. But we can also use Newton's law of gravitation to calculate it, where big M is the mass of the planet and r is the distance from the box to the center of the planet. Now you can see that m cancels from both sides. So the acceleration due to gravity on the Moon or any other planet depends on the constant g, on the mass of the planet, and on the radius of the planet. So you can use this equation to determine g on another planet. Now you might be asking, how important is gravitation and does it get examined? Well, the answer is not very much. The last question on gravitation in the long questions was in 2017, where there were just 6 marks as part of question 2. And 2 of the marks was a recall question, state Newton's law of universal gravitation in words, which we won't look at. For 4 marks, they said a 200 kilogram rock lies on the surface of a planet The acceleration due to gravity on the surface is 6.0 meters per second squared. Calculate the mass of the planet if its radius is 700 kilometers. Now, you should know by now that I normally highlight in red the given information, but you'll see I've highlighted the mass of the rock in orange. Because if you look at the solution from the memo, it's very easy. That is the equation that's given to you on your data sheets. And the g, small g, the acceleration of gravity on the planet, equals big G, the universal gravitational constant, times m, the mass of the planet, divided by r squared. Of course, m is what we're looking for, big M. But we notice that small m, the mass of the rock, doesn't come into it because it's cancelled from both sides. So small g is 6. Big G we get from our constant sheet on page 40. The radius is 700 kilometers, and we need to square that, but we also need to convert to meters first, and we'll get a mass of the planet of 4.41 times 10 to the 22 kilograms. Another question even further back, November 2015, a 4-mark question, very simple, Newton's law of universal gravitation. Planet X has a mass of that and a radius of that. Calculate the gravitational force or weight that planet X exerts on a 90 kilogram rock on this planet's surface. In this case, I have highlighted in red because you do need that. Simple calculation, Newton's law of universal gravitation from your data sheets. Fill in all the numbers, substitute and solve, and the 90 kilogram rock will have a weight of 12.90 newtons. So very few questions on gravitation in the long questions, but examiners love to ask on gravitation in the multiple choice. And you can see some gravitation multiple choice questions on page 69 in your booklets. And you can see here 2 different questions about gravitation. And again, lower down on page 69, 2 more questions, including one from the November 2020 paper and November 2019. Now, these are important and you need to know how to do them, but I'm not going to redo it here because we did this extensively in video 7 and on page 66 in your booklets. We handle this question of ratio questions, and we look specifically at Newton's law of gravitation and how to answer ratio questions. So please, if you want to know more about this, watch video number 7 and look from page 66 in these booklets. So let's look at 3 recent exam examples from November 2018, 2019, and 2020. We'll be looking at question 2 on Newton's second law, and this is our most important equation, F net equals ma. Now, I showed you earlier, this is a snapshot of the 3 questions. You've got 2 questions with pulleys and 1 question on an inclined plane. In all 3 cases, there are forces acting at an angle. You need to make sure that your trigonometry is good. Question 2 can be quite daunting because it counts on average 17 marks. It's a big question, and it's the very first long question you come to. And a lot of matriculants start the exam on a bad note because they are so terrified by this question. I want to tell you to have no fear for this question. And I'll tell you why I say that. Because you can break up this question into 4 parts. And I'm going to show you that in each of these question 2s, there is a free body diagram to be drawn, an equation to be solved, always Newton's second law, an application asking you to explain something, and a recall question. The equation is usually the hardest bit, but even if you don't get full marks there, you can get a lot of marks in these other parts. So on average over these 3 years, the free body diagram counted 4 marks, the equation 7 marks, the application questions 4 marks, and the recall question 2 marks, making up the average of 17 marks. So again, the equation is less than half of the whole question. So don't be fearful. How did pupils do in 2020? Well, on average, looking at a cross-section of pupils, for the free body diagram, the average mark was 81%. So pupils did very well, and that's a good place to start with some marks and get confident. The equation, not so good. The average mark was 49%. Recall question, 62%. That looks good, But for learning work, that should be 100%. But the application explanation's not so good, the average mark being 35%. Now, how can I help you with these 4 sections? Well, the free body diagrams were covered extensively in video 5. And I really want to encourage you to go back to video 5. You can go to page 31 in this booklet. I'm not going to go over that again, but a lot of instruction and practice was given on drawing free body diagrams. Remember, it's not just for those 4 marks, but very often that free body diagram helps to unlock the whole question. The equation, well, that's why we're here now. Video 6.1 gives a general introduction to equations, and this video 6.2 is all about solving the equation in question 2. The application questions, I have to say these videos are not enough. They require a deep understanding of Newton's second law, which only comes by going through the work in your notebook, your textbook, and with your teacher. This 1-hour video is simply not enough, so you need to spend some time making sure you understand Newton's second law. The recall questions, I'm not going to try to help you at all, because that's simply learning work. And I encourage you to learn those, because those are marks that you should get every time. Remember on page 37, we introduced you to this progress method, and we will use this to solve these equation problems. Remember, of course, also always to go to your data sheets. And on page 38, the first page of your data sheets, the second section on force, has these equations. The one you're going to use most often is simply F net equals ma. And so we've divided them up into the one circled in red for Newton's second law, the one circled in blue for friction, and circled in green for gravitation. Let's go to November 2018. I will do this for you as an illustrative exam example. And then the next 2, I'm going to ask you to try them, and then I will go through them with you. So it's a typical question on a table which has a rough horizontal surface. Notice that word, that means friction. You've got an 8-kilogram block connected to a 2-kilogram block by means of a light, inextensible. If you don't know that word, it just means the string can't be stretched. Passing over a light frictionless pulley, and it slides from A to B and to C. Now, I want to tell you, this is a lot of reading to do, especially if you're not confident with English, but all of that is summarized in the picture. So make use of your pictures. Now let's look at the questions, and they fit into our FEAR package. Question 2.2, for a labeled free body diagram, is the free body diagram. 2.1 is the recall question. I've crossed it out, not because it's not important, but because you're going to learn that. I'm not going to do that now. In red, you've got the equation questions for 7 marks in total. And in purple, you've got the application questions, and they're more on the next screen. Now, let's start off by dealing with the application questions, which require us to have some understanding of the system. It says when the 8-kilogram block reaches point B, angle is 15 degrees, and the acceleration of the system is 1.32 meters per second squared. Give a reason why the system is not in equilibrium. It's only 1 mark. That must be simple. Well, an equilibrium system with no net force will have no acceleration. So you simply need to say in words that the acceleration is non-zero, therefore the system is not in equilibrium. We'll come back to the equation, looking at 2.4 and 2.5. Of course, you can find this on page 45 in your booklets. They say, as the block moves from B to C, the kinetic frictional force is not constant. Give a reason for the statement. Remember, kinetic friction depends on a coefficient, which will not change because the surfaces don't change, and the normal force. So in fact, that's what changes here. So these are the application questions. So the normal force changes, and that's because the angle here increases. I will explain it better on the next screen. Let me just deal with 2.5. They say if you replace the tabletop, the horizontal surface, with another surface from a different material, will the frictional force change? And the answer is definitely yes, because the frictional force depends on the nature of the surfaces in contact. So in 2.4, the normal force changes. 2.5 mu, the coefficient of friction changes, because it depends on the nature of the surfaces. Just to show you in pictures an explanation for 2.4, when the block's over there, the angle's 15 degrees, and you can see as it moves closer, that angle will increase. And that's because the normal force will change as that angle increases. So if I just show you what the 15 degrees looks like, if I put that same triangle over here, you can see the angle is definitely bigger. Now you don't need to say all this for the 1 mark, but I'm just trying to explain it to you. And of course, because the angle is bigger, there'll be a larger upward component. The string will tend to lift the block more, which will decrease the normal force and therefore decrease the friction. Let's get on to 2.2, and this is the free body diagram. Now, I'm not going to spend time on this because in video 5, we spend a lot of time on this. For the free body diagram for the 8 kilogram block, it's 4 marks, so we expect 4 forces. First of all, just draw a circle or a box for the body. I'm doing it directly on the picture just to make it clear. But of course, always start with the weight, which is always vertically downwards. Then we have the force of kinetic friction to the left. We have the normal force vertically upwards. And we have the tension force in the string at an angle of 15 degrees. Now, to get your 4 marks, please note this is from the marking memo. Mark is awarded for the label and the arrow. Don't leave out your labels. The length of the arrows is not important. Don't try to draw it to scale. 1 mark is deducted if you add an extra mystery force. Don't do that. And 1 mark is deducted if the forces don't touch the body. And finally, probably the hardest part of the question is the actual equation question. Use the 2 kilogram mass to calculate the tension in the string is the first part of this. Now we're going to use our progress method, which is shown on page 37 and is discussed in detail in video 6.1. So we'll start with a picture. Now a very good picture is given on the exam sheet, so don't redraw it. I would suggest you just add a few things. So we want to look at what's required in green, and that's the tension in the string on the 2 kilogram. It says use the 2 kilogram mass. We're also told that the acceleration at point B was 1.32 meters per second squared. Now, if that's accelerating the 8 kilogram block to the right, it is also accelerating the 2 kilogram block down because they're joined by a string that cannot be stretched, an inextensible string. So we take the 2 kilogram block and we can do a little free body diagram. It has a weight pushing downwards, which is simply its mass times g. It has a tension force pulling upwards. And that's a tension force we want to calculate. So for the 2 kilogram mass, F net equals ma. As I said, that will be your most important equation. So we're taking downwards as positive because we know the acceleration is downwards. You can choose either way, but this is easier. So mg, which is the weight downwards, minus t pulling upwards, is equal to ma. Now, we just need to substitute in, and everything highlighted in red is given to you. And of course, that allowed us to relate what's required to what is given by this equation here. What's in blue is obvious, the acceleration of gravity. So I simply substitute in all the figures that I get from my drawing, solve for t, and we get t equals 16.96 newtons. So that was for 3 marks. Now that figure is going to be used in 233, which is calculate the kinetic frictional force between the 8 kilogram block and the horizontal surface. Once again, our progress method, we have a picture. Let's add what we're looking for, what is required, the force of kinetic friction, which will be to the left, as we know the block is accelerating to the right. What is given, the acceleration of the block, and the tension of the string, we now know because we calculated it in the previous part. And of course, the tension is the same throughout the string because it can't be stretched. Its direction is changed by the pulley. So for the 8 kilogram block, because it's moving on a tabletop, we're only going to consider horizontal forces. So we're not going to worry about its weight or the normal force. We have the force of kinetic friction to the left. That's what is required. We have the tension force to the right, but we're going to take the horizontal component of that, which will simply be t cos 15 degrees. Excuse me. So for the 8 kilogram mass, what's our equation? As always, F net equals MA. And we need to relate what is required to what is given. So we have T cos 15 to the right minus F to the left equals MA. We've decided that movement to the right will be positive. So we know what T is from part 1. We know what the mass and acceleration is, 8 kilograms times 1.32. We simply solve for F, and we get a kinetic frictional force of 5.82 newtons to the left. Again, this might seem like quite a mouthful, but use the opportunity to rewind the video, watch it again, and I'm sure you'll agree you need have no fear for question 2. So let's consider 2 further examples of question 2 from November 2019 and November 2020. Now, it's very important that you actually try these for yourself. I showed you how to do the 2018 question, but it's really important for you to pause or stop the video here. You'd need 29 minutes to answer the 2 questions fully on page 46 and 47. So I encourage you to do that now. So let's start with November 2019. This was 16 marks. Remember, the average for question 2 is 17 marks. Now, you can see there's an enormous amount of written information, and you need to read through it, but you'll actually see that if I just add that vector for friction, that all the information is now summarized in my picture. So pictures are very valuable in question 2, and I encourage you to use the picture in the exam paper, add the information which is not there, and then refer to that afterwards. It's much quicker than trying to read through that. Again, there's that word inextensible, just simply means it can't be extended or it can't be stretched. So once again, is there a fear factor? Well, not for you, but remember there's a free body diagram question, that's 2.2 for 4 marks. There's an equation question, that's 2.3. This is for 8 marks, and this is quite a big one and quite a tricky one. We'll see how you did in a moment. There's an application question where you have to explain something, just 2 marks this time, 2.4. And 2.1 is the recall question, which I'm not going to do because that's learning work for you. Let's deal with the application question straight away, 2.4, and it's quite an easy one. So AB is a rough surface which has friction. BC is smooth where there's no friction. These blocks are being pulled up the slope, and they say if block P is past point B, how will its acceleration compare to that calculated in 2.3? Well, of course, it must be greater than, because there's no friction. And you know there's a force pulling up the slope. If you take away the frictional force, which acts in opposition to motion, then of course the effect of that force will be to cause more acceleration because there's no friction. So that was quite simple. Let's have a look at the free body diagram 2.2. Draw a labeled free body diagram for the 2 kilogram block. Please read it carefully. Don't do it for the 3 kilogram block or you'll get 0. 4 marks, we expect 4 forces. Put a dot or a box for your object. Always start with the weight vertically downwards. Then we have the kinetic friction down the slope. We have the normal force at 90 degrees to the slope, not 180 degrees to the weight. That depends on the slope. And then we have the tension force in the string, which acts up the slope. So 4 marks. To get 4 out of 4, again, you need to take note of these 4 points from the memo. Now, maybe you need to go back to page 33 in your booklet, and this is covered extensively in video 5, and remind yourself of normal forces on an inclined plane. So this object on the plane experiences 3 different forces. There's the normal force, which is always perpendicular to the plane. It has the gravitational force, which is always vertically downwards, no matter what the angle of the plane is. And we have the frictional force. Now that can be up or down the slope depending on which direction the object is moving. Now this object is moving freely, it's not being pulled. And we notice that this weight has 2 components. So it has one, the purple one, which is perpendicular to the surface, and will be equal and opposite to the normal force. Also has one which is parallel to the surface. That's the force that pulls the block down the plane and will be opposite to friction. Whether it's equal or not depends on how great the frictional force is. Now, this big triangle can actually be turned around and slotted in there. You'll see the blue and the white triangles are similar triangles, same angles, same ratio of sides. And so that angle there is theta. You'll see that the perpendicular component is mg cos theta, and the parallel component is mg sine theta. Again, if you're not clear about this, go and look on page 33, revise in video 5. So we really need to consider both the objects that are moving here. We did an exercise earlier in this video, just doing some quick calculations of acceleration. That was fine for the exercise or for multiple choice, but for a big 8-mark question, you need to do it much more systematically, like we're going to do now. So that was the free body diagram for the 2 kilogram, and then we also need a free body diagram for the other mass piece. And of course, the tension is the same, and that's going to allow us to calculate between the two. So because we are looking at an inclined plane, because the objects are moving parallel to the plane, we only want to look at those parallel forces. So we're going to get rid of all forces which are at 90 degrees to the plane. So the two normal forces can go because they won't affect movement up and down the plane. Also, when we look at the weight, we're going to take the component of weight, WP, which is parallel to the plane, and then we can get rid of the vertical weight. Again, the component of the weight parallel, get rid of the vertical one. Finally, the force is at an angle of 25 degrees. We're going to take the component of the force we'll call FP, the force parallel to the plane, and get rid of the other one. Now you can see all our forces are acting parallel to the inclined plane. And so we can use them with our Newton's second law equation. So let's do it for each mass one at a time, starting with a 2 kilogram mass. And we're going to regard motion up the plane as positive. Again, you can choose either way, but we know that these objects are moving up the plane, so it makes sense to call that positive. So for the 2 kilogram mass, start with Newton's law, F net equals ma. I won't go through the whole progress method again as we did in the last one, but we have our picture. We're looking at what is required, and we're going to relate that by these equations. So we've got up the plane is T, Fk and Wp are down the plane, so T minus kinetic friction minus the parallel component of the weight. That's the net force which causes the acceleration ma. So we've got T minus 2.5, you were given that, equals 2 times 9.8 times sine 30, and that's equal to 2a because it's the acceleration of the 2 kilogram mass piece. We just work out the numbers, and we get that T minus 12.3 equals 2a. We have two unknowns here, but it doesn't matter. We're actually looking for the acceleration. We don't know the tension either, but we're going to use the two objects to get rid of the tension. For the 3 kilogram mass piece, F net equals ma, Newton's second law again. So up the plane is Fp, the parallel component of the applied force, minus tension minus Wp equals ma. Fill in the numbers. We were told 40 newtons cos 25 degrees minus T minus 3 kilograms times 9.8 sine 30 equals 3a. And again, when we work that all out, we've got 21.55 minus T equals 3a. Now, can you see we've got two simultaneous equations for T and for A? And what we're going to do to finish off, we're simply going to add equation 1 and equation 2. Now, you can see when we add them, we'll have T and minus T, so that will disappear. We'll have 21.55 minus 12.3, that will give us 9.25, and 3a plus 2a equals 5a. We now have a simple equation for acceleration, and we can solve, and we can say that the acceleration equals 1.85 meters per second squared. What about the direction? The question said calculate the magnitude of the acceleration, and so we finished. Phew, that was a bit of a mouthful, and that's why it was for 8 marks. You might think that you'll never get on top of this, but again, use the opportunity to rewind the video, look at it again. And if you work systematically from the 2 kilogram to the 3 kilogram masses, considering only forces that are parallel to the plane, I guarantee that you'll be able to answer a question like this. And finally, let's have a look at question 2 from the November 2020 matric final exam. This question counted for 16 marks, slightly less than the average of 17. So you're told that you have a 20 kilogram block resting on a rough horizontal surface. Notice the word rough means friction, connected to blocks P and Q, which are stuck together by a pulley, over a pulley by a light, inextensible string. If you don't know that word, it just means it won't stretch. The pulley is frictionless. Force of 35 Newton is applied to the 20 kilogram block, an angle of 40 degrees, and the 20 kilogram block experiences a frictional force of magnitude 5 Newtons as it moves to the right at constant speed. Again, that's very important because that tells us there's no net force acting on it, following Newton's first law of motion. Now, once again, you might look at this all filled with fear, but let's deal with those fears. Once again, there are 4 parts to this question, and we've colored them. 2.1 is the recall question. We're not going to deal with these because we're looking at skills, and you can get that from the memo. That is just learning for you. 2.2, the free body diagram, 5 marks. And actually, the average mark for this was over 80%. So people did very well. And you've already got 7 marks from the first 2 parts of the question. 2.3 was our equation, 5 marks, slightly less than usual, and it wasn't too difficult in this case. And then you've got 4 marks of application, explaining something that's happened by applying your knowledge of Newton's second law of motion. Okay, so we're going to start with the free body diagram. 5 marks tells us we should expect 5 forces. So as usual, we put a circle or a box for our body. Always start with the weight. That's the simplest force, always vertically downwards, no matter what, even on an inclined plane. Then we have the frictional force opposing motion. It's kinetic friction because the object is moving. We have the normal force, always at 90 degrees to the surface. Then we have the applied force of 35 newtons pulling to the left. And we have the tension force in the string pulling to the right. So those 5 forces to get 5 marks. Make sure you have the arrow and the label. Don't worry about the length of the arrows. Don't add any extra forces, and make sure the forces touch the body over there. Now, we're going to go from that to the application questions, the ones that ask you to explain something at the end. We'll come back to the equation. They say at a certain stage of the motion, block Q breaks off and falls down. Now, we've been told that the block is moving with constant velocity to the right. They tell you after a while, block Q breaks off and falls off. So obviously now this mass has become lighter. So how will each of the following be affected when this happens? So first of all, the tension in the string. 1 mark, you just need to choose from increases, decreases, or remains the same. Now, obviously, if this is lighter, it's not pulling as hard on the string, so the tension in the string will decrease. Now, secondly, the velocity of the 20 kilogram block. Well, it was moving to the right at constant velocity, but now the tension force pulling it to the right has decreased. So therefore, the velocity to the right will decrease because there's now a net force to the left, because this tension force, which was exactly balancing the other forces, has now become less. So eventually, in fact, this mass piece would slow down till it came to a stop and then start moving in the opposite direction. Let's look at the equation. For 5 marks, calculate the combined mass m of the 2 blocks. So we have our free body diagram for the 20 kilogram mass piece, and I've drawn the simple free body diagram for the PQ mass piece here. It just has the tension force pulling it up and its weight pulling it down. Now, its weight is the unknown mass, that's what we need to calculate, times g. Now, remember our progress method. We've drawn a picture, and we can just draw on the picture that's in the exam, actually. We're focusing on what is required, and that is the mass m. What is obvious is g, the acceleration of gravity. What is given to us? Well, we're told that the velocity is constant, and that tells us the acceleration is naught. That's important. And then because of that, because it's in a horizontal direction for the 20 kilogram mass piece, we can get rid of the normal force. We can get rid of the weight because they're both at 90 degrees. And we can take the applied force and resolve it into a parallel component there. And you can see the three forces we have acting on the 20 kilogram mass piece are all in the direction. They're all parallel to that constant velocity. So for the 20 kilogram mass piece, we start with our basic Newton's second law equation, F net equals ma. The net force is responsible for the acceleration. Now the net force is T to the right minus force of kinetic friction to the left minus the parallel component of the applied force, and that is equal to ma. Now, of course, we know we've already said the acceleration is naught. So the right-hand side becomes naught. So in fact, this mass doesn't enter into things at all. So it's the tension force, which is unknown at the moment, minus 5. We were told that was the value of friction, minus 35, the applied force times the cos of 40 degrees. All that in orange and red was given to us. So we can make a calculation that the tension force pulling the 20 kilogram block to the right is equal to 31.81 newtons. Now I've shaded it in purple because we're going to carry it forward to look at the next one. So for the block PQ, it's also moving down at constant velocity. Because these two are tied by a string, it also has zero acceleration. And this tension here is the same as this tension, but we're just looking at either ends of the same string. So for the PQ mass, we can say again, Newton's second law, F net equals ma, and m is that unknown mass which we are trying to calculate. So the net force is mg pulling down and t pulling up. So mg minus t is equal to ma. So the unknown mass times 9.8 for gravity minus 31.81 newtons carried forward is equal to naught because the acceleration is naught. And one can easily solve that to get a mass of 3.25 kilograms. So I hope you were able to follow that. Again, if not, simply go back in the video and watch it again. If anyone asks you, how do you eat an elephant? The answer is one bite at a time. And the same applies to question 2. It can seem quite daunting, but if you break it up and you realize with the acronym FEAR, there's a free body diagram, there's an equation, there's an application, and there's a recall question, even if the equation is very difficult, there's a lot of other marks you can get. So don't be fearful about this question. Use what you've learned in this video, practice lots of exam examples, and I'm sure you'll soon come out on top of Newton's second law.